Hey guys, we're doing 12.2 today, transformations to achieve linearity. We're going to start with power models. So in the past, when we've looked at two quantitative variables, we've always used DOFs, direction, outlier, form, and strength, to describe that relationship. And in the past, the form has just been linear or nonlinear. And we might call it curved, something to that effect. But today we're going to learn how to actually use the curve relationship and run a regression. So there are two approaches, the first of which is you can actually fit a curve to the data that you're given. So if you suspect that the relationship is exponential, you might want to run an exponential regression. If you think it's quadratic, you would run a quadratic regression. However, that is not in the curriculum for AP Statistics. We are going to actually learn how to straighten the association, and then we will run linear regression analysis to actually make predictions. So we're going to go through that process today. So what we have here is some data, length and weight, and both are quantitative. So we're going to do a scatter plot of it, and we're going to look at it and analyze it using DOFs as always. But what they want to be able to do here is they want to be able to take the length of the fish and predict the weight of the fish. So let's look at this in our calculator. So go ahead and take a second, enter all this data into your calculator. And I'm going to do a scatter plot. Of course, I want to do list 1 versus list 2. And so I have everything there, zoom 9. So I have a positive, somewhat strong, curved or nonlinear relationship, and there do not appear to be any outliers. So let's go ahead and document that, write that down. So direction is going to be positive because as the length of the fish increases in general, so does the weight of the fish. There are no outliers. The form is nonlinear, and we'll talk about what that relationship may be in just a second. And then the strength is pretty strong, somewhat strong. Now, think about the type of relationship that might exist between length and weight. So what makes a fish weigh more? Well, the length, the longer they are, typically the more they weigh, but also the girth of the fish. So we're going to think of this as a one-dimensional representation for length, and then more like a three-dimensional representation, a third-dimensional for length. So basically, this could be represented with a power model where weight is equal to the y-intercept times length cubed. So weight would be cubic dimension, and then the right side would also be a cubic dimension as well, three-dimensional. So this is a power relationship. So you've dealt with these in math before, where you've dealt with a quadratic or a cube, something to that, or even a square root is also a power relationship where the power would be 1/2. So let's go ahead and see how we could linearize this relationship. So there's two approaches we could take. We can either make both variables three-dimensional, which would be cubing length, and then weight is, of course, already three-dimensional, or we could make both variables one-dimensional, where we take the cube root of weight versus length, which is already one-dimensional. So in either case, you're going to be transforming one of the variables for this particular analysis. So let's go ahead and take a look at what this would look like in our calculator and how we would accomplish this. So I'm going to start by going ahead, and list 3 is going to be list 1 cubed. So I'm going to cube the length. So I'm just going to say list 1 cubed. And then list 4 is going to be the cube root of our y's, or list 2. So that's going to be under math, and it's going to be option 4. And I want to do the cube root of list 2, so I'm creating the cube root of our weights. So that's what we have there. Now you're going to do the same thing, and then we're just going to have to pair it up and be careful as to how we're pairing it up. But we want to do list 3, which is our cubed length, versus our weight. So those would both be three-dimensional. So let's take a look at that and see what that would look like. So I'm going to do a scatter plot. And again, it's going to be list 3 versus list 2. So I have my length cubed versus my weight. And you can see how it's definitely linearized. So that's one relationship we're going to explore. The other is going to be when we actually look at our original length, one-dimensional, versus the cube root of our weight. So in essence, we're turning it into a one-dimensional. Let's see what that looks like. And again, it's also linear. So what I want to do is I'm going to run both regressions. And so let's just go ahead and run one of these regressions. So stat, calc, option 8. And I have in here my cubed length versus my weight. So I'll just go ahead and run this regression. And remember how you can store your regression equation. It's vars, y vars. And we're going to store it in y sub 1. So it's a function. And run your regression. And the things you want to write down every time you run a regression are going to be your y-intercept, your slope, and you are going to want to write down your r-square and r for these because we're going to actually be comparing these models one to the other, like which transformation actually worked better. So we're going to be using the r-square and the r. We're going to be relying on those heavily for that. So let's go ahead and go back in and do a quick look at the scatter plot. And remember, this was our first transformation, which is going to be list 3, our cubed weight versus list 2. Sorry, list 3 is our cubed length versus our weight. So it gets very confusing. You have to actually think about it every single time. So this is our transformation where we cubed our length versus our weight. And I've already run the regression, so the line is going to be graphed right on top of that. So it looks really good. So I want you to do the same thing for the other transformation as well. And let's go back and document all that. Okay, so that's the first scatter plot that we looked at, and it looks strong, or there's a strong positive linear association between length cubed and weight. You have to be very careful that you don't talk about length and weight having a linear relationship. They do not. Length cubed and weight do. So this is going to be the second transformation, also a positive, strong linear association between length and the cube root of weight. And then I ran this regression as well. And then you want to make sure to document both models, and then in particular going to look at your r-square for this. Overall, both transformations seem to be working. Both seem to be linearizing the data. But when I look at the second transformation, it looks a little bit stronger because I have an r-square of 99.8 here versus r-square 99.5 here. They're both very strong models, but the one on the right seems to be a little bit better. So let's just kind of summarize. When you think you have a power relationship, you can achieve linearity by either raising x to the power and relating it to y, or taking x and relating it to the cube root or the fourth root or whatever the power is. You're going to take the root of y, relating those two. So that's how we just did it in the example we just did regarding the fish. But what if you don't know what power to choose? You could play around with it, and actually, if you were doing this in the real world for your real job, you would probably want to do that. But for AP Statistics, we're going to pretty much just use two approaches. The first will be to deal with if you think you have a power relationship. You're going to use logs. You're going to take the log of x and compare it to the log of y. And that can be the common log or it can be the natural log. And you can do it either way. So I'm going to do it both ways today so you can see both outcomes. So we have an example here. I want you to go ahead and enter your data into your calculator. So your x's will be the distance from the sun, and your y's will be the period of revolution. And then we're going to generate a scatter plot, and then we're going to take the log of our x and the log of our y, and I think we're actually going to use ln for this, and then we're going to analyze that and use it to make a prediction. Okay, I've entered my data in the calculator, and I want to go ahead and see what the relationship looks like. So I'm going to do a scatter plot of list 1 versus list 2. And what I see here is a curved relationship, and it's positive, and I don't see any outliers. So I want to take the natural log of both my x and my y and then look at that relationship. So I'm going to go into my list and I'm simply going to go up to list 3, highlighting that, and I will do the natural log of list 1. And then I'm going to do the same thing in list 4, highlighting list 4, but I'm going to do the natural log of list 2. So now I'm going to be comparing the natural log of my x and my natural log of my y. So I'm going to generate a scatter plot real quick for that. So this will be list 3 versus list 4. And then let's see what that looks like. Okay, and I evidently have some sort of equation in here, so let me get rid of that. So zoom 9. And it's definitely more linear, so that's what I wanted to accomplish there. And so the next thing I'm going to do is run the regression. So it will be stat, calc, option 8. And again, I want to make sure I do list 3 and list 4. And let's go ahead and do our regression, store our regression bars, y bars, select function, and it's y sub 1. And then again, what I'm going to pay attention to is the y-intercept, the slope, your r squared and your r. And then I do want to see what this looks like with the line on top of it. So zoom 9. Wow, it's very good. It's going almost straight through the data points. So let's analyze all this and see what we can do with this. Okay, so part A says to describe the relationship between the distance from the sun and period of revolution. So there appears to be a strong positive curved relationship between the distance and the period, and there are not any outliers that I can see. Now we transformed the x and the y variables, and I chose ln. And again, you could use log as well. It's just the very last step that would make a difference into how you use the output. So I'll talk about that in just a minute. So once I generated the scatter plot for ln of distance, ln of period, which I already did, it looks very linear. So the graph of period, ln of period versus ln of distance has a strong linear pattern indicating that a power model would be appropriate, and there is my regression output. So it's a very strong model. Now, part C says to generate the least squares regression line, and here it is. Now, you have to be careful that when you make predictions and you input your x, you have to make sure you take the natural log of that before you put it into the model. And then also, it's actually giving you the natural log of period. So how are we going to deal with that? So we want to make a prediction for an AU of 102.15. So I input all this, I take the natural log of it, multiply it by the slope, add the y-intercept, and the natural log of period is 6.939. What you have to remember is we're solving for period. We want to predict that y. So you have to remember that the base for a natural log is e. So it's really e to this power, 6.939, gives us our period. Now, this is where it'd be different. If I had used log, I would actually get a different model, but I'd get the same prediction because I would take my base of 10 for a common log and raise it to some power to get the period. So that's where it would be different at the very end for making your final prediction. So that is how you would find your prediction if you are taking your x and your y. You input your x, you take your natural log of that, and the prediction is the natural log of period, and then you have to sort of unravel it from the very last step. Okay, that is it for today's video, and you have assignment 4 to complete now. So hope this made a lot of sense, and let me know if you have any questions.